Okay, we're going to have a quick think about how we start off a PLC program and how we start thinking about how to develop some stuff. I'm not going to start off by jumping straight into a PLC. I'm not going to start off by jumping straight to which PLC should I use, what software's best, how do I name my variables, stuff like that. To begin with, let's not even think that far into it. Let's go back a little bit and imagine a couple of parts of this. Firstly, you need to know your program. You need to know your problem. You need to know what it is you're trying to solve and where it fits into the bigger picture, and both view professionally and personally, and for the particular project you're working on. So straight out of the gate, one of the first things people always ask is, what PLC am I going to use? The answer is one that's supported, cost-effective, time-effective, and reasonable to use for the particular project. So you're not going to want a $10,000 Allen Bradley processor for some mixing plant. You're also not going to use a $100 processor that doesn't have Ethernet on it, because they're just a pain in the ass to program. So the other thing to think about is, if you invest your time and your effort and your organization's effort into learning a suite of software, a group of techniques, and the way to use a particular kind of PLC, use one that's industry standard in your area. So in Australia, that's going to be Allen Bradley or Siemens probably. Sure, there are big players in the market, and if you add all of those players up, they take probably 30% of the market. So do you really want to spend your time learning to program a PLC that makes up 5% of the 30% of the market? I would suggest that until you get to the point where you're comfortable with all of this stuff, stick with stuff that's well known. You'll get better resources, you'll get better help. The downside is most of it's much more expensive. The one we're going to look at in a bit in Australia is quite good. Pricing's good, support's good, and I like using them because of the way the software works. I find it quite intuitive. There are aspects of the configuration that are a bit of a pain in the ass. There are aspects of the hardware that aren't perfect, but none of them are. So let's have a little think about something that we're going to design. So if we have a little think about a process, imagine an imaginary machine that we're going to write some PLC code for. The example could be a dishwasher. Most people will be familiar with it. Throw some dishes in, throw a tablet in or some liquid or something, close the door, turn it on, pick a mode, hit start, away she goes. Let's have a little think about this in terms of not so much what my PLC code is going to look like, but in terms of what's a good way to approach that kind of problem. So we know from the dishwasher example, there are only a couple of states. There are only a couple of inputs. We've got buttons on the front. We've got some feedback, whether it's empty of water, time elapsed, things like that. It's a quite simple process. And one of the things that's specific to this kind of process is that it doesn't have an upstream and a downstream process. So it's not a production line. It's not a continuous production. We don't have a machine that loads dishwasher. We don't have a machine that unloads dishwasher that it has to interact with. So in this case, a finite state machine is an excellent choice. There's a couple of reasons, and it's my go-to for OEM style machines, single standalone machines. And the real reason for that is all of the states are easily identified. It's very easy to diagnose and debug. The code can be reusable. It's a particularly robust way to go if you're a beginner. It doesn't solve every problem, and it's not the solution for every problem that you have. But in this case, it's a pretty good starting point. So let's have a quick look at this Visio diagram. Basic flowchart. The process of using a dishwasher. We're going to, when the machine is turned on, we go to idle mode. There's nothing happening. There's a light turned on, power light turned on. The only way we can do anything as far as a state goes from there is we have to pick a mode. Nothing else really does anything. If we pick a mode and we don't do anything, after a time it goes back to idle. But it will happily sit there in idle mode forever and a day. So if we then look at this diagram and we say, from idle mode, where can we go? We make a selection and mode selection is complete. Now if mode selection completes, we either pick another mode. You could press the mode 1 button and then decide you want to go for a longer wash, press mode 2. So we can add a little loop here. It says we can go back and re-pick our mode. If we do nothing for a certain period of time, we go back to idle mode, mode becomes unselected. So we can go around this loop in a number of different ways. But once we've made a selection and we press the go button, the pre-start in this case, Dishwasher is going to do a few things. It's going to check that the door is shut. It's then going to try and purge any remaining water out of the bottom, make sure the pump runs and things like that. And then when that's complete, when that process is underway, when that state is active, there's going to be a couple of things that happen. Either the amount of time prescribed elapses and all of the things worked perfectly, in which case we transition to the next step. If these things didn't work perfectly, we have some kind of fault. The door wasn't shut, the pump failed to run, water level stayed high for too long, things like that. So we then take this pre-start process. Instead of completing successfully, it can then jump to an alarm. So an alarm, like I say, could be excess duration trying to remove water, pump failed to start, something like that. But assuming it does work and all the conditions are met, we then transition to a running state where water is pumped around the inside of the dishwasher, the little thing goes round, all the magic happens inside the box. After an amount of time, that process completes. We could say 10 minutes. So after 10 minutes, the process completes and we go back to idle, the door can be opened. If the process doesn't complete, the pump fails, temperature's no good, water level drops suddenly, unexpectedly, door is opened forcibly, things like that, we jump to an alarm state and we say, okay, this is not normal, this is not what we expect. We're not going to continue to pump water in, for example. We're not going to see the water level drop dramatically, unexpectedly, and then continue to pump water in while the kitchen floods. So at that point, we're going to move to some kind of alarm handling. This is one of those processes where first-time person who's never written any PLC code goes, okay, let's pick a PLC, let's pick a programming language, a programming suite, let's go nuts. Maybe slow down a little bit and have a bit of a think about how you're going to lay this out in a much more abstract sense. How are you going to organize this? Typically what I would suggest is the logical flow for a normal program is to do something like read some information, make some decisions, add those numbers up, subtract them, work out if they're within range, scale them, things like that. And then once you've worked out the information that you read in, completed your mathematical process or your logical process to determine what's going on or what needs to happen, then drive some outputs to make that happen. So I would separate my program, if I were you on a process like this, on a small process, into subroutines, and I would have one for reading field I/O, input-output, maybe a separate one for scaling. So for example, if you've got a 4 to 20 milliamp signal for water level in a tank, for example, I personally wouldn't want to be trying to read 24,762 and try and mentally calculate how much of 32,768 that is as a percentage to work out how full the tank is. I would suggest to you that it would be better to scale that to 70% and then work in your logic with 70% or 71% or whatever the number is, and then scale that back to your 0 to 32,000 number and work purely in numbers or ranges that make sense to the human. We're not really good at doing that math on the fly, and we make mistakes, we make misinterpretations, and in the middle of the night when it's freezing cold and you're knee deep in mud out in the field somewhere in an industrial process, A, you don't want to be making mistakes, and B, you want this to be as easy as possible to diagnose. So scale your analog values. It will make a big difference, and maybe not to you, but the person that follows you will certainly be pretty happy about it. So I would lay my program out somewhat like this. We would read inputs, make decisions, do process, and then drive your outputs to make things in the field happen, and then repeat the process. That being said, if we go back to this and we think about states, for example, you could give states names, you could give them numbers, you could just say that use a Boolean to say next state, next state, next state. You could do it in all number of ways. Think big picture. Think back to, when we're talking about which PLC do I use. Think about your future. Think about the organization's future and where this project fits into the larger scope of things. Are you going to be a person who develops one-off small machines? If that's the case, you probably don't need to worry about this unless you're starting to do, say, food and beverage and you need to integrate with a whole line of equipment. You may not ever need to think about this, but there's no substitute for good practice. Check up on things like the ISA S88 model. Check out PackML. Check out ISA S95. Let's have a little look at some of those things and see how they may play a role in how you choose to connect ML. Let's have a look at PackML, for example. So PackML came about for a number of reasons. There's an entire history here that you can read about. I probably wouldn't drill too far into that for the time being. But it's not a very good picture, but let's drill in and have a look at this anyway. Oops, too far. So PackML talks about transition between states. It exists to give you a common platform of understanding between different vendors, but loosely speaking, you have a bunch of them like holding, completing, suspending, unsuspending, resetting, starting, stopping, things like that. There's diagrams out there for which states can transition to which other states, so you can't transition from, say, holding to unholding directly. There's a held step in between, things like that. So you don't need to be intimately aware of what all of those states are, but be aware that there are standards for those kinds of things. There are numbers that represent different states. For example, if you've got a conveyor system and your conveyor system can't feed product in because there's nothing coming from the previous system, there's a range of state numbers that are pre-prescribed that most people that use these standards will be aware of, and starved for product because of blockage will have a number. Not all of the numbers are specified, so there's many hundreds in a range from 6,000 to 7,000, for example, that you can nominate your own for, but the first couple of dozen from that block will have pre-allocated meanings, and most of those meanings will cover off most of your common use cases. So use those. If you have alarm numbers that represent things like starved or can't feed out because of blockage, things like that, use the numbers that exist. Other people will know what those numbers mean. Generally speaking, if I saw numbers in those ranges and I didn't know what they meant for a particular application, I would just jump on the internet and look them up. So using standardization is always going to be an advantage for you. And that's, again, why you use a PLC that's standardized. It's why you use software that's easy to understand. It's why you use terms and techniques that everybody else can understand. So looking at PackML is going to give you this idea of transitioning from states. And the idea of using a state machine for an example like a dishwasher works out really well. It fits into this. We can simplify it because we don't need suspending, clearing, aborting. We can simplify it a little bit. But the overall idea is still a useful one to keep in mind. And probably the other one, as you're becoming more proficient with larger and larger systems, is the use of a hierarchical model for your physical plant or your logical plant. So for example, having enterprise level, site level, building level area, machine, and then machine component. In fact, the S95 model, I think, calls them enterprise area, or enterprise site area, work center, work unit, and then there's individual machines. So that hierarchical model helps you, make components that are relevant at certain sizes. It allows you to build in a modular fashion. It's much like object-oriented programming in the IT world versus the operational technology world. So use those concepts where you can, and do a bit of research and find out what best practice is. It's going to be hard to do because not a lot of this stuff is well published. Not a lot of it is sort of public domain. If you have a quick look around on YouTube for a video on how to write a PLC program, as somebody who's a little bit more proficient, some of them are really poor. Some of them are quite good. But as a novice, how do you tell those apart? Well, probably the easiest way to think of it is if this person's not thinking big picture, they're not giving you enough knowledge to move from the amateur play world to the professional world, maybe keep looking for more detailed content. I do admit it is going to be hard. It's not a simple thing to find. So moving from that idea of back to our finite state machine. For our example of a dishwasher, we could look at things like the number of buttons we've got, inputs and outputs and things like that. It's for small processes like this, it's quite easy to think about the inputs and outputs. When you get to very large scale things, understanding your requirement specification is going to be more important than understanding your I/O. It's a common trap to go down the path of saying, if I map out all my I/O, it's going to give me enough information to understand what I need to do. I just read it in, do some stuff, map some things out. How hard can it be? Probably a little harder than that in reality. We all do that. We all fall in that trap of going, if I know my inputs and outputs and I've got a vague idea of what I need to do, I just go from there. I would suggest spend a bit more time, a bit more effort on the planning phase of things. Ideally, you're going to spend probably more time planning than you are executing code. As a beginner, you're going to be slow executing code, so you're not going to be able to make that up by doing less planning. You'll never make up the time that you didn't do in planning by writing software fast. Many years of experience, not just myself, but as an industry, we know this to be fact now. There's no argument that if you jump right in because you think you know what you're doing, that you're going to be faster than had you have planned properly prior to starting. So you'll get pressure to start quickly, you'll get pressure to get going, stop wasting time, stop asking questions. Every question you get right before you start will save you 10 times as much effort afterwards. How you manage that with your employment and your situation is kind of hard to do, but we all suffer with it, but we try. So in terms of our dishwasher, let's have a little bit of a look. I'm saying we've got 6 digital inputs. We've got a mode button, like fast, slow, intense wash or something, a start button, a cancel button, and say an input that says the water level is empty, an empty water sensor. And then we might have 4 outputs, a light that says it's idle, a light that says we're in mode 1, 2, 3, 4, an alarm LED, and we want to turn the pump on and off and the heating element as well. So we could call that, say, 6 or 7 outputs, 6 inputs. Initially, straight out of the gate, for what we're going to look at in the next couple of short videos, we're not going to look at the I/O itself at all. We're going to think about how we design the state machine that could run this rather than this specific problem. Seeing a solution to this problem probably isn't really going to help you that much. Seeing how somebody who's got a little bit more experience, and I'm not a great PLC programmer, don't misunderstand and think that what I'm telling you is A, gospel, and B, the perfect way to do it. There are other ways, there are other software, there's other techniques, there are other guys out there that are better at this than I am, 100%. But this, I'm hoping, will give you enough of a position to start that you can think about these things in sort of more context than just following wire this to here, press this, this is a contact, Bob's your auntie's live-in mother. There's more to it than that. So let's start by saying I'm going to use for this demonstration the Beckhoff PLCs. Couple of reasons. Beckhoff really well supported here in Australia. Tech support's good, pricing's good, availability is pretty good. The software I think is particularly good. The ability to simulate the software for a couple of hours at a time without having to buy a license or without having to have physical hardware on your desk is a godsend. So for me, for demonstrating to you, this makes a lot of sense. They're not the cheapest PLCs out there, nor are they even close to the most expensive. The correct PLC for your application, I don't know what your application is. So let's have a quick look at the Beckhoff world. I will blow away all the code that I've just written and pause the video, and then I will get back to you and we shall rewrite some of this stuff.